Hi everyone, I'm Luca Busch and I'm a research fellow at the German Center for Cosmological Lensing at the Ruhr University Bochum, where I'm working primarily with Henrik Hildebrandt and Angus Scheidt on redshift calibration. And today I would like to give you an overview of a recent publication titled KiDS-1000 Cosmic Shear with Enhanced Redshift Calibration. So the primary motivation for this work has been a number of past studies that has shown a rising tension in the key cosmological parameter S8 between constraints that we get from, on the one hand, cosmic shear and the early universe and the cosmic microwave background. So you can see here an example in the projection between the parameters omega m and S8 from a recent study by Asghari et al. That shows you here on the bottom the constraints from lensing and then this ellipse showing the Planck legacy constraints. And one potential reason for this discrepancy might actually be problems with the calibration of this data and potentially unhandled systematics in this calibration. And in particular, we are worried about redshift calibration because this might actually just describe such a shift in S8 that we see here. And therefore in this study, what we did was first of all improve the redshift calibration of this KiDS data by using an enhanced redshift calibration sample, but also studying systematic effects and how they propagate from the redshift distribution all the way to the cosmic shear constraints that we get in the end. So I want to start by saying a few words about the data that we're using, which is from, as I said, the kilodegree survey, or just KiDS, which is an optical imaging survey carried out at the VLT survey telescope. What is special about KiDS is that it has an infrared counterpart, which is called the Viking survey from the Vista telescope. And KiDS-1000, so the particular dataset we are using here, covers about 1000 square degrees, shown here in this footprint plot on the bottom, represented by the blue and green tiles. And our data has a depth of up to 26 magnitude in the R-band, and is selected based on photometric redshifts between 0.1 and 1.2. So now the problem is for cosmic shear and lensing in general that we can't rely exclusively on spectroscopy or just photometric redshifts because they're not sufficiently precise. And therefore we use different redshift calibration methods. In particular in KiDS we use the so-called SOM redshift calibration. So here this is represented by this toy model. On the one hand we have our unknown imaging data set where we have some arbitrary distribution of photometric observables such as colors and magnitudes, and on the other hand our unknown redshift distribution that we wish to calibrate. So now additionally for this method we need a calibration data set, which is typically composed of spectroscopic redshift campaigns. And since the design of these spectroscopic campaigns is typically quite different from imaging, we have to expect that there's a significant difference in the distribution of these observables, photometric observables, and therefore also the redshift distributions. So now the idea of this calibration method is that we employ a self-organizing map, hence the name SOM calibration, to construct a reweighting scheme that allows us to match the distribution of these observables between, on the one hand, the calibration sample and the imaging data as shown here in the toy model. If we then consider the reweighted redshift distribution of the calibration sample, we can use that as a direct estimate for this unknown redshift distribution of the imaging data. So there's one particular problem with this calibration method, and that are cells in the SOM where we don't have any calibration data available. So that means if we look at our distribution of these observables, there will be some excess in our imaging data for which we don't have any corresponding calibration data. So we also can't estimate those redshift of these unknown galaxies. And one way to solve this problem is by what we do in KiDS. We define the so-called gold sample selection, where we basically reject all SOM cells where we don't have sufficient calibration data available. So we essentially cut down the sample size and trade off sample size against potential systematic biases in the redshift calibration. So the second thing that we are interested in is how systematic effects in the Redshift calibration may propagate to cosmological constraints. And therefore we run the whole calibration method using subsets of our full calibration data, which then gives us a new Thorne redshift distribution, a new KiDS-1000 gold sample, so a subset of the lensing sample, and then after running a cosmic shear analysis, parameters such as S8. And then we repeat this analysis by using different subsets of this calibration data and then looking at the variance that we get in our cosmological parameters. So now a few words about the calibration data itself. First of all, we rely mostly on spectroscopic redshifts, and these come from 6 different calibration fields, which cover, for example, the CDFS field, the Cosmos field, but also surveys like D2 and the VVDS field. And compared to previous work, we have significantly extended this combination of spectroscopic redshifts. In particular, I would like to mention C3R2 and the Devils survey here that we have added. But we didn't stop there. We also tried to further increase the completeness of this calibration data by including precision photometric redshifts. And these come either from the Cosmos 2015 sample, which uses 30 broad and intermediate band filters at a significantly higher depth to derive photometric redshifts, and also the PAUS survey, which uses some of these Cosmos filters, combines them with additional 40 narrowband filters to get significantly improved photometric redshifts. But the drawback being that the sample is limited to an I-band magnitude of 23 now. And if we combine these 3 data sets, we always maintain a hierarchy. So we always prefer the spectroscopic redshift. If that's not available, we rely on a PAU photometric redshift, and then finally we take a Cosmos 2015 photometric redshift as our redshift estimate. And this allows us to construct different subsets of the calibration data, as we can see here in this redshift distribution comparison and a comparison table of these data sets. So first of all, this dashed line here represents the previous installation of the redshift calibration carried out by Hildebrand et al., where we had about 25,000 calibration objects, and now our updated spectroscopic data sets has about 50,000 galaxies, so more than twice as large. As you can also see here, adding many redshifts in the histogram. Then next, when we add the PAU data, we see that we have a rather small increment because many of these galaxies are bright, so we already have spectroscopic redshift estimates. And then finally, a big addition is again the Cosmos 2015 data, which give us more than 100,000 calibration objects. So again, more than doubling the size of our calibration sample, and also adding many high redshift galaxies with redshifts larger than 1 to our calibration data set. And finally, there is also this last data set represented by this blue line, which is a subset of spectroscopic data with very high reliability. So redshift confidence of 99 or higher. And that is about comparable to the Hildebrand et al. Original data set, as you can see in this comparison here. So now this brings us to the actual gold samples and their calibrated redshift distributions. That's what you can see here, split into 5 tomographic bins that we use in the lensing analysis. And we see that there are quite some differences at various redshifts appearing, not just in the tails of the distribution, but for example also here in bin 3. And we also see that there are quite some differences in the mean redshifts that we obtain in each of these bins. So now the key question is this actually a change in the calibration of these galaxies? Or is it just that we have additional galaxies in some of these gold samples that we can't calibrate in some of these others because they get rejected by the gold selection? And that's what this plot here can basically show us. In the top we see the subset of galaxies that are common to both our fiducial spectroscopic calibration sample and the sample that also includes PAUS and Cosmos 15. And in the bottom, these dashed lines, we see only those galaxies that are calibrated thanks to the addition of these photometric redshifts. So now we can see that the addition of galaxies is scattered across a wide range of redshifts, and actually relatively small number density. So that means that the majority of the difference between the redshift distributions that we saw earlier actually comes from changing redshift distribution, as seen in the top panels, where we see how this same set of galaxies is calibrated with these two different calibration data sets. So unfortunately, with the data that we have available here, we can't really tell which of these redshift distributions is more accurate, so to say. For that, we would actually need some sophisticated simulated data sets that allow us to calibrate any potential remaining systematic biases in these redshift distributions. So one other thing that is interesting for us is to look at the completeness of these gold samples. So we call this representation, which is the fraction of the complete lensing sample that is included in our gold sample in that case. And looking at the first row here, we see these representation fractions for the Hildebrand et al. Gold sample for the 5 tomographic bins, starting at about 70% and then raising up to 95% in the last bin. So now what we can see is, as we step by step switch to our fiducial calibration and then add the PAUS and Cosmos 15 data, that we first of all increase the gold sample size total by 7% and end up at a plus of 12%. And we see, as we add these additional data, we increase this representation fraction gradually in almost all bins until we reach almost 90% in bin 3, 4, 5, 2, 3, 4 and 5 for our combined Spec C, PAUS and Cosmos 15 sample. And then finally we have this highly reliable spectroscopic calibration sample, which is, as we see again, quite similar to the Hildebrand et al. Calibration set. So now this brings us to the question from the beginning: how do these different gold samples and their redshift calibration propagate to the cosmological constraints in the end? And for that we essentially ran a full cosmic shear analysis using the KiDS Cosmology pipeline, or in short KCAP. So for each of these samples we had to calibrate a multiplicative shear bias, then had to measure the shear two-point correlation functions. Then as primary statistic for our analysis we used the first 5 COSEBI modes, for which we then also had to calculate a matching covariance matrix. And then in the end, for each gold sample we sampled the likelihood function and ran a minimizer to find the best fitting cosmological parameter constraints. And now that's what we can see here on this slide, where we see the constraints on S8. You see now here shown are 2 points for each of these samples, which just represent 2 different ways of quoting parameter constraints that we get for MC-MC chains. I would like to focus at this circular data point and the solid line, which represents basically the best fit and the 96th percentile uncertainty. So the most important data point is our fiducial data set, which is highlighted here also by this purple shading. And we can see that if we compare the added PAUS and Cosmos constraints, then we see that we actually get very similar constraints on S8 in terms of the absolute value as well as the uncertainty on the parameter. Now we can also compare this to a number of literature values. So first of all, we compare to Asghari et al., which is the previous analysis of the KiDS-1000 data, and we see that our constraints are slightly lower compared to that. We also compare to HSC year 1 results and there's year 3, and we see that these are all roughly consistent with each other. And then finally in the bottom now we see the Planck legacy results that you already saw in the very beginning on the introductory slide. And we see that with our extended calibration data set, this tension between these measurements increases slightly to 3.4 sigma in our case. Coming to the second question, which is the systematic variance that we get from our different calibration samples. There we find that no matter what combination of calibration data we looked at, so also here adding samples that we calibrated using only PAUS, Cosmos, or a mixture of thereof, so just using photometric redshifts for the calibration, we find in all cases that the variance in S8 is less than 0.5 sigma, which gives us some confidence that our cosmological constraints are essentially not limited by systematic biases that originate from our calibration sample design. So to summarize this work, essentially we found when we take the spectroscopic data sets and enhanced it with additional precision photometric redshifts, that we were able to significantly improve the completeness of these resulting goal data sets. And this may come with a convenient side effect that it may reduce systematic biases because the completeness and representation of these data samples is higher. However, to actually show this, one would need more sophisticated simulated data sets that allow to calibrate the magnitude of any potentially remaining systematic biases in the calibrated redshifts. And next of all, we found that the different gold samples that we obtained from different subsets of our calibration data are, in terms of S8, all consistent at less than 0.5 sigma. So showing very little systematic variance there. And finally, this gives us some confidence that the S8 tension that we find between the KiDS-1000 data and Planck legacy is confirmed at a level at 3.4 sigma with our updated calibration data set. Yeah, thank you very much for your attention. Now I'm also looking forward to your questions and the discussion during the live session during the actual conference. Thank you very much.